Alright, good morning class. Today we're going to start our last unit, okay, which is on chemical reaction equilibria. And what we're going to do today is focus initially on some of the stoichiometric, variables and things that we typically use for a given reaction to look at what happens to the moles that I initially have, how do they change, and so on. Why do we do that? Because in the end, when I teach you about reaction constants, which are related to the concentrations of what we have at equilibrium. So we need to know those before we get into that so we can use it together. Alright, so what's the main goal here? We're going to relate equilibrium composition of reacting systems to their temperature, pressure, and initial composition. So based on these three, we can determine what is the equilibrium constant. So for the equilibrium constant, it will be a function of these: temperature, pressure, initial composition. And we're going to look at what's the benefit of all this. It's to basically determine if it's really feasible to use this reaction for a process, a commercial process. So if we know what's the equilibrium constant and we know what's the concentrations at equilibrium, then based on that we know what's the conversion, right? What's the conversion we're going to get? What's the yield for this given process? If that yield is good, then I move on to the kinetics to find out what is the reaction rate. So in thermodynamics, we look at what's equilibrium. In kinetics, we look at what's the reaction rates. How long is it going to take me to reach equilibrium? So that's the result of that. So as a starting example, let's say we did some thermodynamic analysis and it indicated that 20% yield at equilibrium is possible. But then you did some economic, math, and you found like at least 50% yield is necessary for you to make money. Otherwise, it's not going to be making you money. So should we pursue this reaction system or not? Simply the answer would be no. Right? So we're going to say no, yield is too low. Then you did some more investigations, and then you found another process. And for that process, you found we can get 80% potentially yield. Then in this case, you would change your mind. You're like, okay, if I get 80%, it's above my 50% based on my analysis. So in this case, there's some opportunity here. So then you would pursue this type of process. So you would just say yes, potential economic opportunity is possible. Alright, so this is kind of the intro slide here. Now we're going to get into actual variables of reactions. Alright, so stoichiometric number, extent of reaction, and reaction coordinate. So these are three variables that we're going to go over today and make sure you understand them so then later on we can use them. So here we write the general reaction, alright, which is the following. We got this coefficient multiplied by A1, so this is my reactant 1, plus second coefficient multiplied by A2, and so on, and then these would be what? My products. Now, why are these written in absolute form? Because the stoichiometric number, okay, if it's a reactant, this value would be negative for my reactants. If it's a product, then it would be a positive value. So the stoichiometric number, right, depends on whether it's a reactant or a product. So when we write it in here as a coefficient, we take the absolute value. Why? Because in the reaction, when we write it, we don't write negative and positive, right? We just take the positive number as is. So that's why we call it the stoichiometric coefficient, which is the absolute value of the stoichiometric number. All right? And then all these A's obviously are, different species. So A1, A2, A3, just different species that are present in my reaction. So let's take this example reaction. We have methane added to water. We get carbon monoxide and hydrogen. So what's the stoichiometric number for methane in this case? -1. Why? Because it's a reactant, right? And its coefficient is 1. So then we just write -1. Alright, so the second one for water, what would the stoichiometric number be?
-1.
Also -1. And then carbon monoxide? +1. And then hydrogen? 3. If inert species, what would the stoichiometric number be? 0. Why? Right, it's not in the reactant side, it's not in the product side, it's not part of the reaction, so then it's simply 0. Alright, so the change in moles for a given reaction, right, which is related to what? The rates, right? In a way it's related to the rate. Rate typically is per time. Here we're just looking at the mole change without time. So change in moles of 1 over the stoichiometric number, okay, would be equivalent to the change in 2 over its stoichiometric number. Why? Because of the balances, right? Not absolute, the actual numbers. Okay, so if it was a reactant, it would be a negative. If it was a product, it would be a positive. Why? Because the change would be the opposite, right? For example, what is change typically as? You get n final minus n initial, right? So for a reactant, this will be smaller than this. For a product, the opposite. Final will be greater. So the negatives here would compensate for that. Okay? Alright, so all of these are going to be equal to d epsilon, okay, where epsilon is going to be defined as my extent of reaction. Okay, so this here, together, the change in epsilon, is my extent of reaction. Okay, so this tells me how much has my reaction proceeded, right? So how much has the reaction proceeded? So in general, this is the general form, you know, the change over the stoichiometric number gives me the extent of reaction for a given reaction. Now we want to find the relationship, right, between dni and d epsilon, which is the extent of reaction. What's the general relationship? Let's just take in general, like I. So here we wrote it as 1, 2, and so on. But if I wanted to write an expression with just dni, how does this relate to this? Right, simply as you said. So d ni is equal to the stoichiometric number multiplied by the extent of reaction. Alright? So this is for any species in the reaction. So 1, 2, and so on. Now, this value here, this epsilon, if we take it as is without the change, okay, this is the reaction coordinate. So that is basically a value which characterizes the extent or degree of the reaction from it. Okay? So, in this case, this is the reaction coordinate. And if you recall, actually, whenever we saw these reaction, energy versus coordinate, we would have like, here's the reactants, then we have like the activation energy, and then this is the product. Here, the x-axis was what? Reaction coordinate. Like, how far is my reaction proceeding? Okay? That's kind of a side note here. So this is the reaction coordinate. And in this case, I'm just going to say this characterizes the extent or degree of reaction. All right. So now what we're going to do is we're going to take this expression and we're going to integrate it to find an expression for what is my current number of moles based on the reaction coordinate. All right, so let's do that. So we're going to have an integration. So we're going to integrate from initial conditions. So Ni initially is going to be Ni naught. So that's my initial number of moles. And then in the final state, Ni is just going to equal Ni. So the number of moles of I will equal my current number of moles. So typically we write it as Ni. So this is initial, this is final. In here, the extent would be what, or the reaction coordinate would be what initially? 0. And then here would be whatever it is. The same. It's not 1, it's just the same value. How far it went is the reaction coordinate. Alright, so we're going to write down this equation, dni equals the stoichiometric number d epsilon. So in here we're going to integrate both sides, from initial to final. So here my change is from Ni naught to Ni, and then here it's from 0 to epsilon. So we do the math here, and we get simply Ni minus Ni naught equals a stoichiometric number multiplied by reaction coordinate. And then if I want to find what is my current concentration or my current number of moles, I just move the initial to the right side. So then we get Ni equals Ni naught plus stoichiometric number and reaction coordinate. Alright, so that's what we get. So now, to find the total number of moles in my system, we would sum up all of the species. So then here, this is for one species. I want to take the sum of all species. So then we just take the summation of that, so we get that the total number of moles n, right? So this is not Ni, it's just n, which is the total number of moles in my system, is going to equal to the summation of all components in my system. What's the current? And this is equal to what? For each one, it's equal to this equation. So we're going to plug that in. So we're going to get the summation of all of the initial concentrations, Ni naught, plus the summation of stoichiometric number times the coordinate. But in this case, the coordinate would be what? Constant. So that I can factor that out here, and this is what we get. Alright, so in this case, we can also kind of simplify this to another expression. So we have here, this here is my simply n, which is what we have up here. Then we have initial concentrations, Ni naught. We can also write that as n naught. So that would be the total of initial moles. Plus, the reaction coordinate stays the same. This here would be what in this case? We just sum up all of the stoichiometric numbers. So we get one number and we just call it V. In this case, this is like a V, but in Greek terms it's nu. But anyway, I'm just going to use a V in this case. Alright, so that's the equation in general. So if I wanted to find, as an example, the next thing we're going to move on is the mole fraction, right? For the mole fraction, I need my moles divided by total moles. So that's what we're going to do next. So that's why we did the summation to get the total number of moles. We have our, species I moles. We're going to divide the two and get a mole fraction. So then the mole fraction, in this case, I'm going to use blue here. We got yi is equal to Ni over n. And simply I'm just going to plug in these equations in here. So we have Ni naught plus Vi epsilon divided by n naught plus V epsilon. So that's simply my mole fraction. For what? For all species in my system. So that would be equal to I equals 1, 2, and so on to all the species in my system. Alright, so far so good. So now we're going to do an example. Reaction CH4 plus H2O makes CO and hydrogen again. Initially, we got 2 moles of methane, 1 mole of water, 1 mole of carbon monoxide, 4 moles of hydrogen. Determine expressions for the mole fractions as a function of the reaction coordinate. So have you seen a question like this before? Maybe not exactly. Okay, so let's go through it. So now, essentially what we're going to apply is this here for every species in my reaction. So to apply that, we want to find what is my total number of moles initially. So I want to find what's this. I want to find what is the sum of the stoichiometric numbers. So epsilon will stay as epsilon. So we're coming up with an expression as a function of epsilon. Alright, so in this case, n naught is going to equal to what? I'll write down there. So it's a summation, right, of all initial constant number of moles. So in this case, it's going to be 2 moles, right, plus 1 plus 1 plus 4. So we get 8. So that's the initial number of moles. We found one part of the puzzle. Next part, we want to find the summation of the stoichiometric numbers. So this is going to be the summation of all the stoichiometric numbers. So we got -1 plus what? -1 plus 1 plus 3. Alright, so we get in the end 2. So now we want to write down expressions for the mole fractions for each one. So we're going to start off with methane. So we write y methane. So YCH4 is equal to what? What we see here, right? So what do we see there? Initial, so 2 minus epsilon, right? Divided by 8 plus 2 epsilon. Okay? So that's pretty much it. So you do the same for all of them. So we got YH2O, we got initially 1 mole, subtract epsilon, divided by 8 plus 2 epsilon. So the denominator is going to be the same for all of them. So then the next one, we got YCO. In this case, CO initially is only 1 mole. It's a product, so we're adding more. Its coefficient is 1, so plus epsilon, divided by 8 plus 2 epsilon. And then lastly, hydrogen. We got initially 4 moles. And then we're going to add 3 epsilon over 8 plus 2 epsilon. Alright? So those are the mole fractions. Let's do another example here. So we have a reaction of water decomposing to hydrogen and oxygen. Initially, in this case, we're writing an expression that's general. Why? Because we don't have any numbers. So what we have is Ni initial, or NH2O, naught, is my initial concentration of water. So I want to find an expression for Yi as a function of epsilon, but also as a function of my initial concentration. Okay? So in this case, what would the answer be? I mean, you start with the same steps. Okay, you do these two first, and then you move on to the fraction. So initially, the number of moles, in this case, let's write this in black. So N naught is equal to the sum of all my initial, species. But in this case, we only have one. We only have water, and that's what it says here. So in this case, it's just going to be simply NH2O naught. Then we're going to find the stoichiometric number, the sum of the stoichiometric numbers. So this is going to be the following expression. So this is going to be -1 plus 1 plus half. So then the ones cancel out, and then we end up with half. So then for the mole fraction, right, expressions, we're going to write YH2O is going to equal to my initial, so NH2O initial, minus epsilon divided by what? NH2O, which is also equal to N naught. So I can write either or. I could have written NH2O also. Then plus half epsilon. Okay, makes sense? So you apply the same thing for the other two components. We have YH2. Initially we have how much of it? 0, so we can keep it blank. And then what do we write on top? So epsilon divided by N naught plus half epsilon. And then YO2 is going to equal to what? Just epsilon? Half. Right? Epsilon divided by N naught plus half epsilon. Alright? Alright, so now we're going to look at fraction of H2O decomposed. Change in moles of water divided by initial mole of H2O, which is basically my conversion. Right? if I take the change, divide by my initial, that's the conversion. Because if I have 0 change, and I divide my initial, I get 0. If I have 100% change, right, then the top and the bottom will be equal. Conversion, x would be equal 1. Okay? So this is my conversion. Fraction of H2O decomposed. All right. So in this case, what would the expression be with respect to the variables that we've been working with? Yeah. So we wrote dn I, right? In this case, I is H2O. So dn H2O divided by, right, n H2O naught, or ni naught, same thing. In this case, right, when I write this like that, what do we get? NH2O minus NH2O naught. Now H2O is a reactant, right? So would this be a positive or a negative? Negative. Is conversion a negative or positive?
Negative.
Conversion. It's a fraction, right? Conversion is either 0% or 100%. It's always a positive number. So because of that, we're going to add a negative, okay, to this expression. So there's a negative here.
There is no negative.
Where?
No,
Just, okay. So in this case, if I expand this out, we're going to get NH2O naught, right? So I flipped it now. Okay. Minus my final number of moles. And in this case, the final number of moles would be a function of the extent of reaction, which would be what we see here, right? NH2O minus epsilon will be my current number of moles. Okay, so we got N H2O naught minus epsilon divided by NH2 naught. Right. So we got this negative multiplied out here, right? Will give me negative NH2O, which cancels out with this NH2O, and then we're left with simply, right, so the reaction coordinate divided by my initial concentration. The change in moles is the epsilon if this is 1.
What?
So the conversion is the reaction coordinate exactly if my initial concentration of the water or the number of moles is 1. If this is 1, then this is equal to this. Alright, so if NH2O, as I was saying, is equal to 1, okay, then the reaction coordinate is equal to the conversion, or the fraction of H2O decomposed. Alright. So now we're going to get into multi-reaction stoichiometry. So initially it was just single reaction. Now we're going to do multiple reactions. And how does the number of moles, how do we track the number of moles for a given species? If we have multiple reactions happening at the same time, each one has its own reaction coordinate, right? Every reaction will have a unique reaction coordinate. They won't all have the same number. They won't all proceed the same amount. All right. So in this case, we're going to define I as, we've been defining it in the previous slides here, as my species. So I would be a species. J will be a reaction. So if I have one reaction, then J would be equal to 1. If I have two reactions, we would have J equal 1, J equal 2, right? So in this case, what we wrote here is max J is the number of reactions, which is, in this case, we're going to call M. And then the maximum I would be the number of species, and that would be N number of species. All right, so for one reaction is what we've been doing. So what we've been doing is simply the change in the number of moles for a one reaction would be dependent on the coordinate or the reaction extent for one reaction. So in this case, it would be my species stoichiometric number multiplied by d epsilon. Now for j number of reactions, what do we have in this case? More than one reaction. All right? So then my change in the number of moles would be equal to the sum of all of the extents of reaction multiplied by the stoichiometric numbers. So it will be the sum of all my reactions. So J will be my reactions. Maybe write this in a nicer J. Okay, and then here we'd have the stoichiometric number for species I for reaction J. Why? Because for every reaction you will have a different balance. Multiplied by the reaction coordinate, or in this case the extent of reaction, so d epsilon j for that reaction. Okay, so every one will have basically this, and we just sum them up. All right? So in this case, for I equals to 1, 2, and so on, up to n, and for j equals to 1, 2, and so on. M in this case. All right, so integrating for one reaction, we simply got that the concentration Ni is equal to Ni naught plus the reaction coordinate multiplied by the stoichiometric number. So this we already derived in the earlier slides. Now for multiple reactions, right, we're going to have Ni is still going to be my current concentration. Ni naught is still going to be the initial concentration, right? Because the initial is not going to be affected by how many reactions we have. It's still going to be the same number. Then to that, we're going to add essentially the change due to every reaction. So this term here for every reaction. Okay, so it's going to be the summation for J, and in this case, the stoichiometric number for species I for reaction J multiplied by epsilon J. All right? So that would be my reaction coordinate. And then to get the total number of moles, we again sum them up. So in this case, N would be the sum of Ni's, right? So this would be equal to N naught plus the stoichiometric number multiplied by the extent of reaction for one reaction. So we showed that earlier in the tables or the slides. Now we're going to write it for multiple reactions. So now we're going to have total number of moles, N, still the same variable, is going to equal to initial concentration. So in this case, I'm going to write the summation of all the species initial concentrations. But then in the end, I'm going to simplify it to also N naught, because N naught is the initial number of moles. It doesn't matter how many reactions I have. It doesn't matter how many species we have. It's still the same variable. But in this case, I'll just write summation for all species I, Ni naught. Okay, which is going to equal to N naught. Okay, that's going to be the same as N naught. Next part would be, what is the change, right, in the number of moles that we have, the total number of moles. So this is going to be two summations, the summations of all species and the summations of all reactions. So this is going to be summation of all species, summation of all reactions. And in this case, it's basically what we have up here. So we have the stoichiometric number for every species in every reaction, multiplied by the reaction coordinate for every reaction. Now this part here, if I take this part and this part, right, together, we would end up with what? So we're going to get rid of the I. If we take this sum I with the VI, it'll just be simply Vj. Okay? So summing these two together is going to give me Vj, which is the sum of the stoichiometric numbers for reaction J. Okay? And then that would be multiplied by epsilon J, which is the reaction coordinate. So in this case, it simplifies to plus summation for every reaction, and then we have Vj epsilon j. Okay, so that's for multiple reactions. And then for the mole fraction, okay, simply again following the same methodology, we have Yi equals Ni over N naught, which is equal to Ni naught plus Vi epsilon divided by N naught plus V epsilon. So I took this and I took this and just divided them, right? So then for the multi-reaction system, again, you take this, divide by that for every component. So in this case, we're going to write down, maybe draw a line here. So we have Yi equals Ni naught plus summation J Vij epsilon j divided by N naught plus summation J Vj epsilon j. So this I is specific for the mole fraction of I. So where here? Yeah, there is an I here. Yeah, I did. It's right here. Where? Here? It's there. It's there.
No, تحت النوت آخر واحدة.
This one?
Yeah.
Yeah, that's the sum. So we got rid of that one by taking these together, and I wrote like this here is J.
So we need to solve for each reaction first.
So this would be the sum of VI's in reaction J. And if I had like A plus B makes C, this is one reaction. Let's call this reaction 1, so this would be J equal 1. So then it would be the sum of the VI1 for all species I, so it would take this -1, +1. Okay? You get it? Okay. Alright, so let's just erase that. Alright, so now we're going to do an example. Okay, in this example we have simply 2 reactions. So we have methane and water again, making carbon monoxide and hydrogen, and then again methane, but 2 molecules or moles of water, making CO2 and 4H2. N initially is 2 moles of methane and 3 moles of water. Determine Yi as a function of epsilon 1 and epsilon 2. Why? Because now we have 2 reactions. So what would be the first step in this case? Right, so we're going to find what's the initial sum of moles that we have. So this will be the sum of all species that we have in our system. In this case, we have 2 moles of methane and 3 moles of water. That gives me 5. Alright, so we found that. What else do we need? Right, so we need VI, but for 2 reactions. So for the first reaction, let's say J equals 1. We want to find VI 1, or simply, what? V1. Because we're trying to find V1, which is the sum of the VI's for the first reaction. So this is going to equal to the summation of all species I, VI for reaction 1. So that J in there is 1. So what is that going to equal? -1 plus -1 plus 1 plus 3. So we get 2 again. And then for the second reaction, again this would be V2 equals summation all species VI reaction 2 equals -1 plus -2 plus 1 plus 4. Again we get 2. Alright, so we got the initial number of moles, we got that. Now we can go directly to this expression, right? Why? Because we have, these, and then For the rest, we can plug it in, depending on the species that we have. So in this case, let's start with methane, YCH4. How much methane do we have initially? 2. And then for the first reaction, how much is it getting consumed or is it being produced? So its stoichiometric number is a negative, right? And it's -1 multiplied by what? Epsilon 1. So that would be the first reaction. Second reaction, consumed, also same amount, so epsilon 2, divided by, what's the initial concentration? 5, right? Because this is what we have here, initial, right? Plus the summation of Vj epsilon j. So in this case, we have 2 and 2, right? So we're going to do what? Right. Plus 2 epsilon 1 plus 2 epsilon 2. So this represents the total change in moles in my system as these two reactions proceed, right? And then this represents what is my concentration of methane at any given time as a function of the reaction coordinates. So far so good? Okay. So you guys seen this? Kind of? Okay. Alright. So then YH2O is going to equal what in this case? 3 minus epsilon 1 minus 2 epsilon 2, 5 plus 2 epsilon 1 plus 2 epsilon 2. Alright? And then we'll do the next 3 here. So we have YCO. So carbon monoxide, initially we have 0. And then we're only producing it in which reaction? First reaction. So then we're only going to have epsilon 1 divided by 5 plus 2 epsilon 1 plus 2 epsilon 2. Then we have YCO2. So what would the numerator be here? So carbon monoxide, CO2. 0 minus epsilon 2 plus. You're producing CO2, right? It's a product. So then it would be a positive, and in this case it would be simply epsilon 2 over 5 plus 2 epsilon 1 plus 2 epsilon 2. Alright, and then the last one, hydrogen. In this case, hydrogen is being produced in both the reactions. So in this case, we would write what? Right. 3 epsilon 1 plus 4 epsilon 2 divided by 5 plus 2 epsilon 1 plus 2 epsilon 2. Alright. So now you guys know how to come up with the mole fractions given a certain reaction, okay, based on the reaction coordinates. Okay? And the reaction coordinates would be typically what we will know if we know the equilibrium constants. So for a given reaction, if I know what's the equilibrium constant, I know at equilibrium what is my extent or what is my reaction coordinate. So based on that, I can also know what's the mole fractions, and based on that, I can also know the amounts given initial concentrations. Okay, so we're going to continue next class, okay, on this unit, and we're going to move towards deriving expressions for the equilibrium constants given this data, and we're going to obviously move towards Gibbs free energy, where the Gibbs free energy change at equilibrium would be 0. Right? When you reach equilibrium, the change in Gibbs free energy would be 0. When you're not at equilibrium, right, you'd have some type of spontaneous change in a specific direction. All right? All right. Thank you guys, and we'll see you next class.